Hi, everybody, again, and welcome to Physics 10. Today is March the 25th, and today we're going to be discussing temperature, heat, and basically thermodynamics. Okay, thermodynamics is a fascinating subject. It has applications, first of all, everywhere. It has applications, of course, in physics. It has applications in engineering. It has applications in chemistry. It has applications in biology. It has applications even in the economy and other fields that are not necessarily science. It even has an influence, if you wish, or an impact on philosophy and religion. There is a lot of debate using some of the stuff that is actually in thermodynamics about those things. Okay, so it is an important topic, and you really cannot do anything in life if you really don't, or at least you cannot understand much of what's going on if you really don't have a full understanding of what thermodynamics is. First of all, temperature. We have an intuitive notion of temperature. We can tell if it is hot or cold. This is intuition. And that's how we started this subject, by the way. We started it based on intuition. We have an object that is hot, which is an object that is cold. I mean, cold in this case is basically a poor name of, say, describing the same thing. It's still hot, but this one has less temperature than the first one, basically. Less hot than the first one, that's all. And then if I bring a third object now, I notice that this third object is actually less hot than the first one, but it's actually hotter than the second one. And I bring a fourth one, and I notice that that fourth one is actually less hot than the second one, which means that it's less hot than the third one, which means also that it's less hot than the first one. I bring a fifth object in here, and I notice that that's actually hotter than the second one, but and also hotter than the third one, but less hot than the first one. It gets messy if I try to describe things this way. I mean, imagine if I have 23,712 and I want to rank them in terms of how hot and how cold they are. It is a nightmare. So we really needed a number to append to it, okay? We needed an idea so that we have append to a number and that's it, and walk away. So the next time I go to the next item, I have another number appended to it, another number, another number. Now, if I really want to compare between two of them in the list of, I don't remember what I said, 35,712, then in this case, all I have to do is just pick the two from that bunch and I see the numbers. They will tell me the story. So I really don't need to do I don't need to go into a place that is going to be very hard to describe. So this is the concept of temperature. Of course, we need to understand the relationship of temperature to heat, which is critical in this case. We need to have distinction between the two. And finally, how these things work. Here is the deal. Science of thermodynamics is kind of strange science. It was basically invented in the wrong order. So Mr. Carnot, Sadi Carnot, in the early 1800s was wondering, basically, he was an engineer working for the French army and working on trains, basically. And he wanted to understand what is the most efficient. I'm not there yet, okay? Don't worry, Jacob, okay? I'm not sharing anything on the screen yet, okay? I'm gonna get the PowerPoints, okay? I'm just telling you the background, basically, of the story. Make sense? Good? Okay, very good. So basically the point being in here is that he asked a simple question. Mr. Sadi Carnot asked, what is the most efficient engine? For that, he basically said the following: grant me the following, that heat does not spontaneously on its own, without any help, leave a cold source to a hot source. Normally, heat will move from the hot source to the cold source. That's natural. Take a cup of coffee, for example, that is just from the oven or from the stove, whatever you cook it on. It's hot. It's going to cool down over time because it's in contact with the air. So in the sense, in this here, heat left the coffee into the air. So in this case, that's normal. Can the air, which is colder than the coffee, lose heat to the coffee? That he said, grant me that's not going to happen on its own. Okay. You tell me, how about the refrigerator? Well, the refrigerator doesn't happen on its own, because you take, for example, something and put it in the refrigerator extracts heat from it and dump it outside. So the refrigerator now does the work. So if you have it, leave them on their own, that's not going to happen. So that is basically an idea that he asked to be granted. I mean, you could do the same thing. You could take, for example, an ice cube and put it in the air. And in this case, the heat will leave the air into the ice cube and will melt the ice cube. So that's still the same thing. So in other words, the heat is still leaving the hot source, which is the air in this situation, back to the cold source, which is the ice cube. So grant me that, he said, I will prove to you. I'll show you the most efficient engine. Well, people realized that Mr. Carnot was onto something. So they said, okay, this is actually something nice. So we can start this subject. It turns out there is a far more fundamental idea before this one, that people realize that it cannot really be the first law that we have to use. We have to call it the second law. So Mr. Carnot came up with, although his idea was first, what is later on called the second law of thermodynamics. Then they came up with the first law of thermodynamics, which states that the energy is conserved in any process involving thermal, exchange of heat. So they said, okay, that must be first. What Mr. Carnot stated about the heat not spontaneously leaving a hot source, a cold source to the hot source, but always from the hot to the cold, must be the second law. They walked away, and this body of knowledge started to accumulate, and they said, oops, we really need another law before the law of conservation of energy. So now they already have stated the first law that Mr. Carnot discovered as the second law, and then the one that they stated as being the first law about the energy. So they needed a law before that. So in this case, they said, how are we going to do it? Are we going to basically reorder everything and put the third law as being the first law, and the second law discovered, keep it as second, and the first law as third? No, they didn't do that, because at that time, the two ideas were very much solidly, structured. So they kept the first law discovered first as being the second law, the second law discovered second as being the first law, and the third law discovered basically, or stated at least, I should say, was being now the zeroth law. So thermodynamics is strange science because it was discovered backward, basically, in this sense. It was postulated backward. You start with the last and you go all the way back to the beginning. So we have three laws in thermodynamics: the zeroth law, which allows me to do thermometers, basically, which we're going to be talking about today. Then we're going to talk about the first law, which is the law of heat exchange and work and internal energy and things like that. And then the third law, or the second law, I should say, in this case, which the one I stated already, and that has to do with a big topic now in philosophy, has to do with something called entropy, and order and disorder. So let's get into the notes now and see if we can get some ideas through, some stuff through this thing. So again, we're doing chapter 15, which is about temperature, heat, and expansion. Materials, actually, they expand on their own if you put them under stress. If you pull on them, or you actually increase their temperature, that's one of the two. So we're going to explore the idea of temperature. This is based on the zeroth law. Okay, heat, it's related actually to the second law and the first law. And then specific heat, each material has its own specific heat. Basically, they take this piece of iron, and we use it a lot. This tungsten here. It has a low specific heat, meaning that I don't really need a lot of heat for its temperature to rise higher. All I have to do is just a little heat, and then the temperature starts to go higher and higher. Unlike water, for example, and some other substances, you need to dump a lot of heat in it to start to see barely the temperature rise. So materials have this property. They call it specific heat. Specific heat is specific to the material in the sense that some materials tend to have easily their temperature change with heat. You remove a little of their heat, and then they go down drastically. They cool down. You heat them up a little, and the temperature rises skyrocketed. Okay. If you go outside, for example, on a cool day, and you have two benches, one that is made out of wood and one that is made out of iron. Which one, or steel, or I'm sorry, aluminum. Which one do you think is colder when you sit on? There are two benches. It's a cold day, okay? And you're tired and you want to sit down waiting for the bus. You look around and there is one that is made out of wood, basically, and one that is made out of aluminum. Which one is colder?
Aluminum, right?
Okay, some people are saying aluminum. Who thinks it's the wood? Which one would you rather sit on a cold day? I mean,
Aluminum.
aluminum is colder, okay? Is that what you guys are saying? There is a consensus in here. Anybody else going for the wood? No? Okay, let me tell you something in here. It's not aluminum. Aluminum is not colder than wood. So I eliminated one option. So which one is colder, from the aluminum bench or the wood bench? And I'm telling you, aluminum is not colder than the wood bench. Okay, change the wood. Okay, how about the other guys? Okay,
Yeah, that leaves wood.
so you still have only two options.
Wood.
It's not the wood either. So you have two choices. Which one is colder? Actually, there is a third option. Okay, aluminum is not colder than wood, and wood is not colder than aluminum. So they must be
They're equal.
the same temperature. Very good. That is actually the discussion item in here. Why are they the same? Because they have been sitting in there exposed to the same amount of air. So for a long time, so the air was cooling them or warming them in the same time. So they are absolutely the same. Obviously, one of them feels cooler than the other one, and that is because of its specific heat, that's all. When you sit on the bench, in this case made out of wood, the wood does not extract a lot of your heat in this case from you, so you feel warmer, you feel kind of nice. That is basically what it is. It has to do with heat, this one. It has not to do with the temperature. The temperature is the same. But if you sit on the aluminum, in this case, what happens, it extracts a lot of heat from your body, and you feel that heat leaving you in the form of cold. Does this make sense?
Yes.
Okay,
Does
very
now.
good. Okay, very good. I know some of you were puzzled. I mean, if I don't have the option for aluminum, which has sounded obvious, it looks like it's colder, then it must be the wood, but now the wood is out of the question because they are actually, both of them are in the same temperature because they have been exposed to the same elements in terms of weather. So they must be in the same temperature. And the only reason why you feel colder on the aluminum is because heat is leaving you faster to aluminum than on the wood. That's basically the reason why. Okay. So this is item of the discussion. Where is my pen? Let me share the screen again.
So the question is, which one is colder? That's the discussion.
Yeah, you have two things. Aluminum, and wood. Those are benches outside, exposed to them. Okay, which one do you feel colder? Which one? I'm trying to basically colder. The answer is both are the same temperature. One of them feels colder than the other because of the fact that heat is leaving from your body, because your body, I'm assuming that when I said cold day, that the day is colder than you. You're probably well wrapped up and everything like that, so that's not to lose much heat to it. That is basically the reason why you're feeling so cold. So now you decide to wait for the bus, and it's taking a long time. You'd rather sit on a piece of, the bench that is made out of wood. So which bench in here? Probably these are benches, okay? So which bench is more preferable for you? Obviously, the one made out of wood. On a hot day, it's the same thing. Yes. the question is, this is an item discussion. On a hot day, it's the same thing. You don't want to sit in the aluminum because a lot of heat from the aluminum will go into you and you will feel actually warmer. Okay. Whereas the wood, a bench of wood would not have a lot of basically heat, basically sending it to you. It's actually has to do a little bit more with thermal conductivity than thermal specific heats, but that is the point in here. Okay. The point being in here, actually, which is very, very important, is the fact that, what is my slide, is actually, it has to do with temperature. Objects that are under the same conditions for a long time, when they reach thermal equilibrium, they have the same temperature, whether it's being a bench made out of aluminum or another one made out of wood. They are the same temperature, although one of them feels colder than the other, and that has to do with heat, not with temperature. Okay. And then we're going to talk about thermal expansion, as I said, and this is true for all materials, regardless of what they are made up, or whether they are mineral, metals or concrete or whatever that is. Okay. So again, temperature, it's a number that corresponds to the warmth or the coldness of an object. I mean, we have that intuitive notion. Okay. We can basically feel it, and if we put a thermometer in this one in here, we're going to get a higher reading than this one. Obviously, this one is somewhere in between. Okay, so that's basically how this one goes. So it's measured by thermometer, is a per particle property, no upper limit, definite limit on the lower end. Okay, so what that all of this thing means. Temperature, first of all, was observed to not go below, it cannot go below 273.15 degrees Celsius. This is actually an absolute zero. Nothing can be colder than this number, number one. As a matter of fact, nothing can be as cold as this number. This is actually an upper, nothing can reach this temperature. This temperature, you can be slightly warmer than this, but not below it, not actually equal to it too. So this is something that has been observed, and then we can actually justify the reason why that is, okay? So that is one thing. Now, there is absolutely no upper limit to it. The temperature in the heart of the sun, for example, is about anywhere between 20 to 100 million degrees Celsius. Other stars could be double that much in their course. So the temperature can be super, super high. So, but this is a lower limit. So it has no upper limit that we know of, at least, okay? But it has a lower limit, and this is the limit for it. It cannot be colder than this number, okay? And it's basically the property of how fast the constituents or the particle that make up the object are moving on average. As a matter of fact, it's the average kinetic energy of the particles that make up the object. Let's say, for example, gas, okay? Let's put the gas inside a container. So I have gas in here. We know now gas is made up of molecules. It doesn't matter which gas it is. Let's take, for example, nitrogen gas, okay, N2. Nitrogen gas is made up basically of two atoms. Each molecule is made up of two atoms of nitrogen, basically connected with one another. So in this case, you have a, what is the valence of, it has, nitrogen has seven electrons in the outer shell. Anyway, you can think of them that they're forming bonds in there between them, 3 bonds, basically, what you may call them, covalent bonds in here, and it is stable, it is fine, okay? So we have a nitrogen molecule in here, and we have a bunch of them. Actually, we have about an Avogadro number of them, about 10 to the power 23 of them per mole. Okay, so they are moving on average. This one is moving this way, this one is moving this way, this one is going up, this one is coming down, this one is going to the left slightly, this one is going to the here, this one is going super fast, this one is going to here super slow, and so on and so forth. The average kinetic energy, when you take these velocities and you square them, that is the square of the velocity. You multiply it by the mass and you multiply it by half, That is the kinetic energy of every one of them. You average this quantity, where the mass is the mass of these molecules. Each molecule has about 14 nucleons, has about 7 protons and 7 neutrons. That's 14 times 2, that's 28. So you have 28, and the mass of each and every one of them is about 10 to the power 27, negative 27 kilograms. So it's a very tiny mass, this number is, okay? It's a very, very small number. It's about, even when you include all of them, it's going to be a little over probably 10 to the negative 26. It's still a big number. I mean, it's tiny number, small number. So when you multiply it by the velocity, some of them are barely moving, some of them moving very, very fast. So when you average the quantity, you're going to find it the same. That is what temperature is. So it's this kinetic energy averaged. That's all. That's why there is a limit to it in the bottom. Because if you keep on lowering the temperature, that means the particles in the nitrogen gas, they start to slow down, slow down, slow down, slow down, to a point where they are almost frozen. They can never be frozen. That is where that temperature of 273 is coming from. That when the atoms at that point are practically frozen. I cannot really say that they are frozen, because even at those low temperatures, there is a little bit of motion, okay? And that motion has to do with the quantum effects. That's why this temperature is actually a lower limit. But that temperature can be, how should I say it? It cannot be reached because you cannot have something completely frozen. That is the moral of the story, okay? These are the 3 phases that we know on a daily basis, we have experience with. We have gases, we have liquids, and we have solids. And each one of them has basically how the temperature, what the temperature measures. And here, how fast the gas molecules are bouncing to and fro, basically usually the sides in here, okay? That is their temperature. So if you put your hand, you stick your hand in the air, that is basically you're being bombarded all the time by this gas molecules. That is what your skin feels, okay? Liquid, how fast the particles of the liquid jiggle in and out, okay? They are moving also. And then in the solid, again, this is the jiggle motion, but in this case, also followed by the vibrations of the different components. That's what temperature is, okay? So this is what the temperature is. Thermometer is a device, basically. This is how the thermometer works. I take, for example, water, frozen solid, connect to it a thermometer, and call this thermometer 0 degrees Celsius. If you don't like it, you want to call it 32 degrees Fahrenheit, that's fine. We don't care, okay? Then start raising the temperature for this frozen solid, basically ice, or water at 32 degrees, and then wait until the time that this starts to boil, okay? Call this one 100 degrees Celsius. Or if you don't like this number, call it 212 degrees Fahrenheit. That's fine. Now, take this device, which is now a thermometer, and bring it to another object, okay? This is a third object now, and connect it to it. So they have to have thermal equilibrium for me to do this. So in order for me to do this one, I have to have them in contact and reach that equilibrium for me to say that this is where the 0 is and this is where the 100 is. Or if you don't like it, this is where the 32 degrees Fahrenheit is and this is where 212 degrees Fahrenheit is, okay? Obviously, between 0 and 100, it's kind of nice because you can have this graduation between 100 pieces, like the meter, for example, divided into 100 centimeters. This one, the scale is divided into 100 pieces. So the difference between each point and each point is just 1 degree. Here, it actually has 180 divisions, okay? Finer divisions. So it has 180. So in this case, the change in this temperature of 1 degree corresponds to slightly, almost 2 times in here. So this one will depict slight variation in temperature as opposed to this one, which doesn't. So this is the centigrade scale or Celsius scale, whichever you want to call it, centigrade. And this is actually the Fahrenheit, okay? Now, if I take my device now, after I properly calibrate it and I have everything working with it, doesn't matter which one, I bring it in contact with this one and I see that it reads this number. This one actually, it says it's 27 degrees Celsius, and in here is some number in here. Let's say, for example, I don't know. Let's say, for example, it's 83, okay, degree Fahrenheit. It doesn't matter. What I'm saying in here is, if I take this water and raise its temperature from 0 degrees Celsius all the way to where I can see the scale was 27 or 83, that is my correct conversion in here. That is the number in here. That's the temperature of this guy. So this is really relies on something called the Zeroth Law of Thermodynamics, and says the following. If system A, which is this guy, I'm sorry, which is this one, this system A, is in thermal equilibrium with system B. Thermal equilibrium, that means they feel the same temperature. This is system A, this is system B. And system A also is in thermal equilibrium with system C, another one, which is this guy. So this is C, this is B, this is A, okay? Then systems A and B are in thermal equilibrium. That's what this zeroth law says. So that means that I can infer the temperature of this system based on this one, and this becomes just like a middleman. So it's like a measurement device. So now I can take this thermometer with me and carry it all over the place and start measuring temperatures. So how it's made internally doesn't matter. I mean, alcohol, whatever makes it, that is another detail. But the point being, now I have a measurement for the temperature instead of, and I have solved my dilemma in the beginning when I was doing hotter, less hot, between this, that, which was kind of nightmare after you reach probably 3, 4, 5 items, let alone 32,712. I like this number for some reason today. It's sticking in my head. Okay. So again, we use, at least in the in other cultures, or a lot of the cultures in the world, they use the centigrade. And people in the United States in here, and I don't know if there is any, I think that in Britain also, they use this Fahrenheit system, okay? Again, this freezes at 32, water freezes at 32 degrees, and in here it's a 0 degrees Celsius. Here, it freezes at it boils at 212 degrees Fahrenheit, and in here it boils at 100 degrees Celsius. That's the only difference between them. Obviously, the graduations in here on the Fahrenheit scale are much, much finer than the graduations on the degree Celsius, okay? And that is basically a detail in here. Now, in addition to that, now we have another scale that is actually used by the scientific community, used in physics especially, which is the Kelvin scale. So the Kelvin scale is another system in here that relies on the following experiment, basically. So this is the temperature in degrees Celsius, okay? And this is basically the some gases. So what I do in this case is the following. I take a gas. Hold on, guys, okay? I think I have people in here talking. 1 second, okay, please. Sorry, guys, okay, about the disruption. Anyway, so what we have in here, we have the pressure as a function of temperature for some gases that have meet a certain specification in terms of their density and pressure and so on and so forth. So basically, if I take gas 1 and start changing its temperature is going to change, and I have this relationship between the pressure and temperature. This is temperature, okay? If I take another gas, for example, I have this dependency. If I take a third gas, for example, I have this line and so on and so forth. What they did in here is that if I extrapolate the data, I find that all gases seem to have no temperature, no pressure at this temperature of negative 73.15. That is why we shifted the scale from 0 degrees Celsius down to this temperature. This is where theoretically the pressure drops to 0. Of course, doesn't mean anything for the pressure to drop to 0. That's why we cannot reach that temperature. In the lab nowadays, we can reach extremely low temperatures, 0.00 something Kelvin, but we cannot really have 0 Kelvin. There is a limitation to it. You cannot do it. It's impossible. So this is the Kelvin scale now. So again, on pressure, but now this distance now is on Kelvin scale. So the Kelvin scale, which does not have a degree, by the way, appended to it, is a unit to measure the temperature shifted by shifted by 273. So the boiling temperature will be 100 on top of that, so it's going to be 373. So that is the only difference in here. So it's shifted by 273 compared to I mean, we approximate the number to 273 because we really cannot even reach that limit too. It's very hard to do, okay? So this is how the different scales that are, the three scales that are people use commonly. In science, we stick to Kelvin in all relationships, basically, all expressions. We use the Kelvin scale. We don't use the degree Fahrenheit or the degree Celsius. And we usually also, not usually, it's like a unit. We don't say degree Kelvin. It's not a scale like degree in here, how many degrees went up and down. This is actually like a unit, like a meter or kilogram or something like that. Because any temperature above the absolute zero, this is where the absolute zero Kelvin now is a temperature. It has some value. So T is always positive in Kelvin. It's always greater than zero. As we said in the beginning, it has this limit, which is 0 Kelvin, which is negative 273 degrees Celsius, but there is no limit in here to it. It can be any temperature you like, okay? So that's how we arrive to the scale, to this scale. So there is twice as much molecular kinetic energy in 2 liters of boiling water as in 1 liter of boiling water, which will be the same for both. Okay. There is twice as much kinetic energy in 2 liters of boiling water as in 1 liter of boiling water. So basically, you take a boiling water, and let's say you have 1 liter in here, and this is 2 liters of boiling water. Obviously, this one has more kinetic energy, has more molecular kinetic energy, basically, because now we have a lot of water, that's all. We have twice as much than at this point. But both of them must have the same temperature because doubling the amount in here keeps the average the same. Because if we all care about is the average, that is what the whole idea for temperature is. It's the average, okay? Average temperature. So when you double the amount and you double the kinetic energy, then in this case, the two cancel from the numerator and the denominator and you still have with the same thing. No, thermal energy, this one has more kinetic energy on average than this one in the content. So this is not correct, okay? Of course, if we eliminate one of them, so this is not correct. And since we know one of them, this is not correct. So the correct answer is A, because that's an average. So it's like, for example, I don't know, trying to think of an example in here. 2 out of 4 people, for example, are, I don't know, 1.5 meters or higher in height, okay? That means if I don't bring 4 people, but if I bring 10 people, then I don't really have 2 in this case. I will have 5 out of. So in this case, the average is still the same. This is 50%, and this is 2 is 50%. And that is exactly what the temperature is measuring. It's measuring the average of this molecular kinetic energy. So if you double the amount, you really are not doubling the temperature. The temperature is the same. As a matter of fact, another key word in here that is used is boiling water. Boiling water. So that is the temperature is actually 100 degrees Celsius or 373 Kelvin or 212 degrees Fahrenheit. It's the same thing. They have the same temperature in this situation. Does this make sense?
Yes, it does.
Okay, very good. Okay. That to say that a body A has a higher temperature than a body B is to say that it has actually more energy per particle. You could take a nail that is red hot, so hot that it's red actually in color, made out of iron, and you can take a bathtub, for example, full of water, normal room temperature. In this case, the bathtub will have more internal energy because it's more of it. And it has more mass because it's more of it. And I don't know what you mean by this one. This has no meaning in this case because it needs interaction between two things to mean something, okay? Then the nail, both the bathtub and the nail that is red hot, in this case, this has more internal energy because it's more of it, albeit it has less temperature than this one that has high temperature, okay? And more mass, of course, for sure. But this one is hotter in this case, has a higher temperature because of the fact it has on average a higher kinetic energy per molecule, per particle in it. That's why. That's why it has a higher temperature. Heat is an internal energy transferred from one thing to another due to a temperature difference. So basically heat is an exchange of temperature. That is basically what it is. Exchange of heat, I'm sorry. It's exchange of energy. This definition is not quite right, okay? I don't like it very much because you don't really necessarily have to have, even if you have a difference in temperature. This one is T hot. I'm sorry, T hot. I was going to write it in French for a second. I'm sorry. And then this is T cold. You could exchange energy in this case, not necessarily in the form of heat, okay, through work. I have an engine in here. Where are they? A bunch of engines. Actually, this is one of them. I should have really brought this demo in here. I'm sorry. Should have brought some ice and demoed this one, okay? That works with heat, actually. Right now, it's not running because it does not have any heat in it. Remind me, guys, next time to do it, okay? This one actually uses this principle to exchange heat, okay? This uses something called an isothermal and then an isobaric. And even in isothermal, it doesn't work. There is an entrance of heat without difference in temperature. Okay, this definition is bad. Heat is an exchange of energy, period. One way of exchanging energy is good. That is, I know the book will ask you for this one and probably a lot of the questions will be in there. So maybe you can stick to it, but let me explain to you what I mean by that, okay? Heat is a form of energy transfer that can occur due to this difference in temperature. Yes, that is true, but not always true. Yes, okay. It's an exchange of energy, but there is other ways of also exchanging energy. It's not always just heat. I mean, so for example, if the gas expands, it can do work. So work also is another similar in a sense, but not necessarily the same. Another way of also doing it is doing work. As a matter of fact, this is an engine. I have actually another engine in here that right now dismantled, but hopefully I'll put it back together again. This is actually another engine in here that if you warm up this side in here, you put heat in here and you burn it, then it's going to work, and you will see this on its work. And then I had actually the mountain here where I put the motor, electrical motor, and that electrical motor generates electricity. So they're indicating that in this case, heat is converting to work, and work actually, that's exactly what motor is. So work is also another way for the gas, because there is a gas in here that goes through this chamber between these two cylinders. Maybe I should stop the, okay. So what's going on in this engine actually is the following. You have in here gas, and there is an exchange of heat in here through this gas. And there is actually another cylinder in here. Actually, it comes out in and out. Okay. And that's in here and there too. And I'm supposed to have an electrical motor in here mounted. And that electrical motor, I'm supposed to hold it with this one and in place, and then I'm supposed to generate power with it. Anyway, I'm working on this, okay? So this is actually called the Stirling engine, okay? This one also is a Stirling engine too, by the way, the one I was showing you in the beginning too. And this one uses the same principle, except now it's really, you don't have, it looks like I only have one cylinder, but there are two of them. There is actually in the bottom one a cylinder, and in this one actually is also another cylinder. So this is another cylinder. Both of these engines are actually 4-stroke engines still, okay? Both of them are used for processes to accomplish what they need to do. So this one works a lot easier with just the ice, basically, it can work. Okay, the other one requires like burning something in there. Usually I use alcohol, 70% or 90% basically concentration of alcohol for that thing to work. So hopefully I will have them ready next time around. Anyway, so let's continue. So heat, yes, is an exchange of energy and it's a process. And like temperature, which is a fixed thing, you can have an object with the same temperature. It has a definite temperature, but it does not have heat. That's the second point in here that I want you to really be aware of. Where did I put my pen? Did I lose it now? Amen. Here. So that's the second item in here. An object can have temperature, but no heat. It can lose heat or gain heat, but does not have heat per se. I know that's a common word we use in the culture, in everyday applications, but no heat, but can gain or lose heat. Yeah. So it can gain heat. Its temperature will go higher, or if its temperature doesn't go higher, the pressure actually can change in it. So it doesn't have to just be the temperature. So the pressure also plays a role in here, and the volume actually can expand too. So there are other ways for it to translate that. It's not necessarily heat. I mean temperature. So temperature and heat are connected, but they're loosely connected, and you really need to make that distinction. So an object can have temperature, but no heat. It can never have heat. It can gain heat or lose heat. When it gains it, it translates itself in other quantities like temperature or, which is the common thing that we associate. That's why we tend to connect that, or pressure, increase in pressure, or for example, expansion or something like, or compression or something of this nature. Okay. However, heat, if you're going to between two different temperatures, heat transfer between the T hot and T cold in this fashion. So if you only have a hot source and a cold source, then heat will go this way. Okay? Uniquely, in this direction and this direction only. So this is spontaneous. You ask, okay, what happened in the refrigerator? Well, in the refrigerator, you take something like, for example, a cold beverage, and you put it in the refrigerator. It's cold already. So what the refrigerator does from it, in that case, it extracts from it more heat and makes it colder. And dump that heat in the back of the refrigerator. If you go back to the refrigerator, you feel the heat that is coming from the cold stuff that is inside the refrigerator. So the heat will extract heat from, the refrigerator will extract heat from the cold source and dump it outside where it's hotter. But that requires work, requires energy. You have to pay for it. Actually, the refrigerator works to do that. A heat engine like the one I was going to showing you, that does the other way around. It takes heat from the hot source and give you work out of it. Actually, the thing turning or the electrical energy, and the other one actually is work, is energy that you're going to gain and use it for other things. Okay, And that is actually how your engine at the car works. Your car engine is most likely an auto engine. Okay, Otto, after the German guy who basically discovered the process. Or it may be a diesel engine, which is after the name of the guy also who, that's another engine also that is out there used. This is for heavy equipment. Usually we use diesel engines, which is different diesel cycle. And that is the name of the guy who discovered it, actually. And the Otto engine is the name who discovered it, not AUTO, but his name has an OTTO in it, okay? And like the engine I was showing you, that is actually a Stirling engine. And that's very hard to do in real life, but it's a fun engine to work with. And it's actually a lot better, more efficient than this too. As opposed to the most efficient engine, which is Mr. Carlos' engine, which is by far better than any of these ones, but it's very hard to do in real life. That's why it's the best. I mean, because it's theoretical only. I mentioned the quantity of heat. The quantity of heat is measured in joules or calories. Mr. Joule did an experiment on that. Basically, he took a container of water because the heat was defined. First of all, people believe that heat somehow a fluid because you take a cup of hot coffee, for example, put it outside and you see the smoke coming. You see stuff coming off of it. So they thought, and actually you have a feel for it. If you touch the coffee, you feel the warmth coming in your hand. So they had this intuition that maybe it's a fluid. They called it the calorific fluid. That's how the word calorie came in. Then Mr. Joule showed that actually it is not a fluid, it's an energy. All he did was put a container of water, basically, put in it brushes, and then connect them to a string to another mass that falls. He knows exactly how much energy is coming from the fall of that object. It's MGH, basically, potential energy. And then he measures the temperature of how much the water temperature went, because we define the calorie as basically the amount of heat given to a liquid of water to raise for 1 kilogram basically of water to raise its temperature by 1 degree from 14.5 degrees to 15.5 degrees. And that is actually what we defined as being 1 calorie. Okay. You take 1 kilogram of water, or 1 liter of water is about 1 kilogram, sitting at 14.5 degrees Celsius, and you add to it this 1 calorie, and you will see that the temperature has reached 15.5 degrees Celsius. Then in this case, you say, I added 1 calorie of heat, okay? Obviously, this is hard. I mean, this is different than if you take, for example, 1 gram of water. So this is water, okay? Sitting at 14.5 degrees Celsius, and you watch it go by 15.5 degrees Celsius. So in this case, we define it as not 1 calorie, but rather it's 1 calorie. Okay? You guys see the difference between the two. This one actually is in lowercase c, this one in capital C. But the difference between 1 gram and a kilogram is 1,000. So 1 calorie is actually equal to 1,000 calories. Lowercase c, uppercase c. And then people later on appended the unit of the energy to him, and this became as the joules, and this is how many joules are in a single calorie, and this is actually how many joules in another calorie, the other calorie, 4,180. Okay, joules. So that is the conversion rates between them. So you have to be very, very careful when you look at food items and it says calories. What it's really saying is 4,180 joules, not for every single calorie. It's a lot of energy. So taking a piece of candy equates to a lot of energy. How do we know that? We used to do this experiment actually on campus, where we take food and we burn it actually and see how much the temperature of water goes up, and then we use the conversion factors in there and measure the energy for which that happened. And that's how you do it actually too. So when you go to your favorite store to buy stuff, look at the label. Look at the label. See how many calories that food has. Is it something you would want to really have? Because per serving, it tells you how many calories you have. And it could be surprisingly very high number, okay? On the discussion item, which is the biggest item of the day, You are supposed to go home. Actually, I took pictures of 3 stuff that I have at home. And I looked at the words in there that how many calories in them. One of them, I believe, was 40 calories. And that's almond milk. The other one was a vegetarian butter, which was like 80 calories. And the third one was mayonnaise, which was like 90 calories. All of them has the first letter capital, calories. This one also has the same spelling. Both of them are spelled correctly. This one, they tricked you. They put everything in calories. So everything is in caps. You might think that maybe this is a lower C. If it is a lower C, that means it has 0 calories practically. But it is not. They just basically wanted to get by the fact that they wrote the first letter capital, but they wrote everything else capital too, because they need to comply with the law. These ones are in compliance already. So your task is the following. Locate, how many items in the discussion? You found it already? Yeah, 3. Okay, very good. So you're supposed to locate 3 like I did from your kitchen, from your refrigerator, okay? And upload them. First of all, you're supposed to say if they're in big C or properly spelled, basically. They need to have the first letter to be stated in capital C, no matter what, okay? This is a tricky thing they wanted to do to you in here, but it's still they're in compliance because the first letter is capital C. That means this number is correct. 90,000 calories or 90 times 4. Can you imagine? That's about 360,000 joules per serving of that mayonnaise. It's a lot. It's still, even with this almond milk, it's still a lot, 40. But the point being in here is it's a price you want to pay. Is this something that you really want to do? I mean, you might enjoy it and say, I don't care. I like it. Okay. So the idea is in here, were you surprised by the amount of calories in it or not? And if so, are you going to make any changes or you don't care? I like it. I enjoy it. That's my favorite food anyway. So when you talk about it, what are you talking about? That's fine too. Okay. And then you're supposed to reply to your peers on it too. Is this item clear? I think the prompt is in detail in there on the discussion board on this day. Yes?
Yes.
Yeah.
Okay, very good. So let's continue sharing the screen. So you're supposed to do that task. Okay. So all of this question has to do with heat and basically the fact that your specific heat has to do with how much basically temperature. So if I go back to that expression, for example, the amount of heat usually was used a symbol Q for it. The mass of the item, how much mass? Of course, if I bring more, like a bathtub, for example, full of water, and I want to warm it up, it takes a lot of heat from me. Versus if I take a small cup does not require a lot of heat to warm it. So the amount of matter matters, okay? Times also how much temperature I want to go. This is the final temperature and this is the initial temperature. If I want to raise it only slightly high, I mean, it's kind of cool a little bit. It's just below my taste. I just want it a little bit boosted. I don't need a lot of heat. But if I want to increase it so high it boils, it's water is already frozen, I have to wait a long time for that heat to transfer itself from the hot source basically to it so that it gives me that final temperature. So the difference in temperature matters. And then times something that is specific to each element. This is the specific heat. Some materials are much easier to change their temperatures than others. If you have a high specific heat, you can achieve this change in temperature. If you have low specific heat, you can achieve this change in temperature much easier, because even with low amount of Q, you can realize that because C is small, because this will be dividing by that, of course. So if I divide by Q by MC, now it makes more sense. This is the change in temperature. So the change in temperature is higher if I have a lot of heat. That's true. If you have a lot of heat, you can make the change. Or you have less mass. You have smaller amount of mass, you can raise its temperature also, even with the little heat you have. Or you have low specific heat. If you have low specific heat also, you can make that change even for a large amount of mass in here and for a finite amount of heat. You can also achieve that too, okay? So this is basically what this expression is saying. Water, by definition, has one. Remember, we defined the calorie as being 1 gram of water when we change the temperature from 14.5 to 15.5. So this will be 15.5 minus 14.5. That's going to be 1 times the mass of the water, which is 1 gram. This is by definition calorie. So C for water is 1. Any other material has usually less than 1. Water has this unusual property in that it has a very high specific heat. In other words, you need a lot of heat to raise its temperature, okay? If you take your soup, for example, from the oven, it takes a long time to cool down. If you take the soup, for example, and put it in another container, and watch the two, the container, for example, that was made out of metal, like aluminum, for example, it's going to cool rapidly versus the soup that is still cooling down. Because soup in this case, which is mainly water, takes a lot of, has a very, very high specific heat compared to aluminum. So in this case, aluminum is colder, it's room temperature very quickly, whereas the soup, no, it takes a long time. And that is usually what hurts when you eat hot food, not hot spicy, hot food, because of that heat that retains in the liquid, which is in there, okay? So again, takes 2 minutes to raise the temperature of an iron pot of water to boiling temperature, takes less than a minute to raise the temperature of the same quantity of water in a silver pot, because again, silver has less specific heat than iron. So its temperature rises higher to transfer that to the water. In this case, in the case of silver, of course. Silver is a better conductor of heat. So equal masses of different material require different quantities of heat to change their temperatures. This is exactly what I was talking about in here. For the same masses, equal masses, so for the same kilogram of mass of something, you need more heat or less heat depending on the material to raise its temperature with the same amount. That's what this thing is saying. So 1 gram of water requires 1 calorie of energy to raise the temperature by 1 degree Celsius. 1 gram of iron requires 1/8 of that to do the same thing. You don't need 1 calorie, you need 1/8 of a calorie to do the same thing. So therefore, water absorbs more heat than iron for the same change in temperature. Water has a high specific heat. It has an unusually high specific heat. So it has a higher capacity for storing energy. It involves more degrees of freedom actually than the motion of the molecules. Here is the importance for it. It comes into weather because Earth has a lot of water on its surface, so its temperature is more or less regulated by the oceans that is out there. So, and this is true, actually more true, especially, it has a lot of influence, of course, on the weather. And if you compare land, for example, to water, especially if you happen to be near the sea, this is what's going on. During the daytime, the temperature in here, the heat is received the same on the surface of the Earth, regardless of that point at least. So the water is receiving an amount of heat and it raises its temperature barely. Versus land in here, which has low specific heat, its temperature will rise higher for the same amount of heat. So land is warmer than the oceans in this case. And the breeze now will flow in such a way from the hot to the cold, and then basically get rid of that heat, and you will feel actually better. During nighttime, it's the opposite, because there is no sun in here to warm anything, so the air is cooler. So in this case, heat escapes both the water and escapes the land in the same amounts. Whereas the temperature in here need to, because heat is escaping because of interaction with the same air, the temperature doesn't change much in the ocean versus the temperature in here that changes drastically, because even with the tiniest amount of temperature, this will change a lot its temperature. So now the breeze flows in the opposite direction and it actually regulates the land. So which has a higher specific heat, water or land? Obviously, water has more specific heat than land. So this is basically what the importance of the water in this case for the weather phenomenon. Thermal expansion. I mentioned already the fact that materials expand on their own because of the pressure on them. Heat involves also another pressure, and materials actually expand and contract because of this change in heat. If the temperature goes up, they become longer and longer. If the temperature goes down, they become less and less. And this is actually true for anything, for all materials actually. That's why you see the sagging of the power lines, because in the winter there is less temperature, so they rise up a little. So as an engineer, you have to be very careful with that, not to make them too tight, because during the winter they will pull and they will snap. You don't want that. Also, the same thing with train tracks. You need to leave some gaps, because in the winter weather they pull back, but during the summertime they come closer. So if you make them very close from one another, the tracks buckle and the train basically will get into an accident. Same thing actually with the freeway lines too. Even with concrete, they have these gaps too because of the same thing. Concrete and iron has very close thermal expansion coefficients, and that's why we use concrete in the construction, for example, because of the fact that concrete will expand because of heat, and so is iron. So iron is a good material to be used in construction because of this property, because of its coefficients of thermal expansion, very close from concrete. If I use different material, for example, lead, it's not going to work because the concrete will expand more. Actually, the other way around, the lead will expand more and basically start to cause damages to the concrete. That's during hot time. During colder times, it's going to pull back and leave those gaps and causes the whole structure to come apart, basically. So that's why we have to use iron. Iron has its coefficient of thermal expansion. It's very, very close from that of concrete. So as a civil engineer, usually you're testing these materials under a lot of stress conditions, including temperature changes, okay? This is an example of a buckling of a road in this case. Look at the train, the poor train, because of high temperature. Seems like somebody didn't do his homework or her homework. This property is useful also in the sense that we can use them actually for gauging temperature. So because if I put different materials with different thermal expansions, and if there is a difference in temperature, for example, rising, the material that has the less coefficient of expansion will expand more than the material that has the higher thermal expansion, the lower thermal expansion. So when it expands more, it's going to bend one way or the other. So if there is less temperature, it's going to contract more. So this can be used actually as a device to measure temperature. So bimetallic strips are used in heaters to basically disconnect the circuit. So if the temperature becomes too high, you disconnect it. Or if you want it to actually connect to go back into the AC unit, you're going to have it in the opposite direction and those sort. Oven thermometer is also the same thing, refrigerator and electric toasters, in addition to the fact that they're actually used as gauges too, to measure the temperature. So in here, they use like triggers, basically. The case of water was really a unique structure because water, under normal circumstances, yes, you have van der Waals forces, but there's a very limited interaction between the different molecules. Only with the immediate neighbors where you have interactions. When it solidifies, these interactions are more organized and they span through a lot of number of atoms, basic molecules that way, and they became a solid ice. The gap, the spacing between them is higher than in the case of the liquid. So the density now is actually less in the case of solid than in the case of liquid, which is kind of backward. Usually we tend to think that a solid is denser than a liquid, but in the case of water, it works backward. That's why the ice floats. It does not sink. There is about 90% of it that is below the surface, but about 10% of it is still above the surface, which is kind of interesting in here, because if it was the other way around, if ice behaved like everybody else, the oceans will freeze from the bottom up, and that's not good for the marine life and for the basically the plants and for the entire life cycle on Earth. Actually, it could be devastating for life in general on Earth. So the fact that water has a property is actually a very good thing. So it's a useful property. Again, this is description of what I was talking about. This is the fact that its density is the highest actually in here, because it shrinks the most, and then it starts to grow, and then of course it grows too with the temperature rising in here. So this is basically some of the properties of the water. Ice, of course, floats, and its density is about 90% that of the water. Okay, so this is the content for today's chapter. Don't forget your assignment on this one. So I'm hoping that I will have a lot of response for this one. And I'm still debating the exam. Most likely right now it's headed toward the spring, after the spring break, okay? That is where we're headed with it. So the content, for sure, up to chapter 15, we still have another 2 weeks, I guess. So most likely that's where we're going to stop, but I will let you know exactly which chapters are included in the exam by the time we're done with it. Okay? Sounds good?
Yes,
Yep.
sounds good. Professor,
Okay.
for the discussion board of the 3 items that we have to get, you want us to upload a picture of those 3 items as well, correct?
Yes, please. Yes, that would be very nice, very helpful. I'm not requiring that 100%, but I'm really hoping that you do that, because I know that some of you probably will not have access to some of the technology, cameras or something, but I'm hoping that you support your findings, okay, with the picture, okay?
Okay, thank you.
Okay, no problem. Let me stop the recording.